either in Singapore or Delft or in the US. So yeah, so let me try sharing my screen first. Can you see my screen?
Can see.
Yes?
Yes, can.
Okay, perfect. Yes, so today I want to talk about one of the processes I've been working on, mostly at Arizona State University, but also already in Delft and still a little bit at Boskalis. It's about ground improvement using microbially induced desaturation. And in other words, how we can use burping bacteria to mitigate earthquake-induced liquefaction. On the background, you see a result of this process, which are calcified gas bubbles. And I will show you in this talk how we can try to use that for ground improvement applications. So if you have been following this series, you have already received an excellent talk by Professor Jason de Jong and Mike Gomez, and also by Professor Edgar Zengen, and they tell you what biomediated ground improvement is. So it is trying to use biological processes which are occurring in the subsurface to catalyze a chemical reaction, which we can use to change the mechanical properties of the soil. And then these properties, they may vary, maybe the permeability, the stiffness, compressibility, shear strength, or volumetric response which you like to change. But you can do that by forming different products. And the products which most people have been focusing on is biominerals, trying to cement sand using mostly calcium carbonate minerals. And many people have looked into that and with sometimes great success. Other people have looked into biofilms, mostly in relation to reducing the permeability. But today I want to talk about mostly biogas and how we can use biogas in ground improvement applications. So if you know the process, the next step is how can we understand the process at the small scale and eventually bring it up to the field scale. So also that is something which I will discuss today. The process which we'll be talking about is microbial denitrification. This is a process in the nitrogen cycle. This is the natural nitrogen cycle where bacteria in the ground or in plants can fix nitrogen from the atmosphere, turn that into ammonia, and eventually ammonia is a nutrient source for other bacteria which convert the ammonia back into nitrate. And then eventually nitrate, once it's in the soil, it's again a fertilizer or nutrient for plants and other bacteria, which then convert the nitrate back into nitrogen gas. So this nitrate to nitrogen gas is a reduction of the nitrate, and it goes in multiple steps. So from nitrate to nitrite and eventually back to nitrogen. In order to reduce the nitrate, you need an electron donor or an organic carbon in this case, which will be oxidized. And if you use, for example, acetate as the carbon donor, you produce carbonate ions or inorganic carbon, which remains in solution. And if you do that in presence of calcium, you will precipitate calcium carbonate. So if we use calcium acetate as carbon donor and calcium source, and calcium nitrate as the source of nitrate, we can produce biomass, calcium carbonate, nitrogen gas, and CO2 gas simultaneously in one single metabolic reaction. So back in the days, almost 15 years ago, we did some experiments mostly focusing on the carbonate precipitation, which we've considered using denitrification as an alternative for urea hydrolysis, which is used more often in biocementation studies. We felt, okay, this may be an alternative, and it may be good because the nitrogen gas and the CO2 which are formed are maybe less harmful than the ammonium chloride, which remains from the hydrolysis of urea. So we demonstrated in experiments that we could form simultaneously biomass by crystals and biogenic gas. But we've also found that it's a relatively slow process. So we did one column study, which we had to percolate for about 100 days to get an average of 3% calcite. And we had to use relatively low concentrations to avoid toxicity, because this process, if you use high concentrations, the nutrients may be toxic. Also, we found that the distribution of calcium carbonate was quite heterogeneous throughout the column. At the top of the column, we had about 10%, but quickly going down to 3%, and beyond 1 meter, there was actually no calcium carbonate, or less than 1% calcium carbonate formed. So still a lot of work to do. Regarding the toxicity, so this is actually the reduction of nitrate goes into 5 steps. It goes from nitrate to nitrite, and the nitrite is reduced to nitric oxide, and further to nitrous oxide, eventually to nitrogen gas. So both nitrite and nitric oxide can be toxic for the bacteria. So you want to avoid accumulation of these intermediate products. And actually nitrous oxide is a strong greenhouse gas, so also this you want to avoid from happening. If you now use high concentrations, several of these steps, which all involve different enzymes, are inhibited by the presence of these intermediate compounds. So to avoid this inhibition and accumulation of intermediate compounds, concentrations need to be low. And actually we've done some batch tests here, which demonstrate how much nitrate is formed depending on the initial substrate concentrations. So here we found that to avoid accumulation of intermediate nitrate and also nitrous oxide gases in the liquid and gas phase, our concentrations of nitrate should be around or below 60 millimolar per liter of nitrate. So having done that, we felt, okay, still we want to improve our process. Let's try to cement the soil with low concentrations. So we actually varied the concentrations. We had 50 millimolar calcium nitrate with 60 millimolar calcium acetate, doing 3 flushes, and 3 flushes of these concentrations would eventually result in about 1% of calcium carbonate formed. If you just add the amount of calcium and presume that everything converts to calcium carbonate minerals. So we did 3 flushes of 50 or 15 flushes of 10 to end up with both about 1% calcium carbonate. And we flushed them in 35 days. So 3 flushes in 35 days of high concentrated substrates, or 15 flushes of low concentrated substrates. And actually here we showed in these experiments that the amount of calcium carbonate formed with the low concentration is actually much higher, about 0.7% from the 1%. So it's about 70% efficient. But the low concentration results in higher yields of calcium carbonate than the high concentration. And this is due to this toxicity of the high nitrate concentrations. Even with these low percentages of calcium carbonate, we could see an increase, which is the yellow or the orange line, increase in Young's modulus, or an increase in deviatoric stress for the treated columns in comparison with the untreated columns. And looking at the sample of the ascent column, we actually found very large calcite crystals, well, very large, 30 micron, but about the same size as the grains, or slightly smaller size than the actual sand grains it was filling in. On the other hand, you see very little calcium carbonate crystals as compared to other processes like urea hydrolysis, which are much faster. Another feature we saw when we had to apply these multiple flushes is that upon flushes, gradually the hydraulic conductivity is reducing because of the accumulation of both the biogas and the biominerals, but also because of the desaturation of the gas. And because of this reduction in hydraulic conductivity, we had to increase the water head during flushing. But you can see here that in some cases after 4 flushes, the hydraulic conductivity reduced by a factor 1000, almost 3 orders of magnitude. And then we really had to push hard to remove the clog and then start and continue flushing again every time you see this red line. So clogging and accumulation of these products are really affecting the result of multiple flushes. So When we found all these difficulties when flushing multiple flushes to aim for calcium carbonate, we felt like maybe we can use the biogenic gas by itself as a ground improvement method. And we were not the first ones to think about that. That was actually Professor Chu and his student Jia He, who did a lot of pioneering work on the microbial induced desaturation work. And what they showed in large box experiments that you actually only need a very small reduction in the degree of saturation to see a significant reduction in pore pressure buildup when shaking a loosely compacted box, a box with loosely compacted sand. And if you reduce the degree of saturation to 80%, you almost see any pore pressure buildup in such a shaking sand. So these results indicated that, yeah, maybe we can use desaturation, just the biogenic gas itself, as a product to mitigate earthquake-induced liquefaction. So if you have a fully saturated soil, you start to shake it, well, it may contract and the water wants to squeeze out you, so you build up pore pressure and the soil may liquefy as a result of that. So the idea was if we can now partially desaturate the soil, fill the large voids with gas bubbles, because the gas is compressible, you start shaking, you will not build pore pressure buildup, you will not build up pore pressures. So therefore, you can prevent liquefaction from happening, and in that case, you can consider these gas pockets are actually acting like an airbag, taking up the blow from the cyclic movement and then dampening those pore pressure buildups. So with that in mind, colleagues at Arizona State University, at Kavazanjan and his students and other professors, they pitched the process of microbial induced desaturation and precipitation as a two-stage process. So first, you would desaturate the soil. This would give an initial resistance against liquefaction, but perhaps the gas would vent away or gradually diffuse away, and then you could apply multiple cycles to eventually have a more stabilized protection against earthquake liquefaction by the precipitation which you would form. So with that in mind, we said, okay, that is a nice concept, a nice theory, but how can we now predict the treatment performance? How do we know how much we need to inject? How much gas will be formed? Can we actually predict mechanical and hydraulic properties as a result of treatment? How are these products distributed, and how is that all dependent on heterogeneity of the soil which we encounter? And so this was the starting point when I moved to Arizona State and started to do research on this topic with my students over there. So first we said, well, we can actually predict what will happen or how much gas will be formed because we know the reaction stoichiometry. And this is a lot of chemistry here, but in general, you can state that the reaction stoichiometry depends on the growth rate. When bacteria are growing very slowly, they actually convert calcium and acetate, so acetate and nitrate in a fixed ratio, which is the ratio which you can derive from balancing all the elements and balancing the electrons which are transferred in the redox reaction. So this reaction, the catabolic reaction, generates the energy for the bacteria to grow. So if you then incorporate the growth of the bacteria, which is expressed by this equation here, or this molecular formula, then you can actually calculate based on thermodynamic theory what the stoichiometry would be for maximum growth. If the bacteria are very happy and growing using all the energy generated from the first reaction to put that all into biomass, you can calculate the overall metabolic reaction. And so you can actually calculate the ratio between all the products, calcium carbonate, biomass, nitrogen, CO2, and water, as a function of the growth rate of the bacteria. So if they're very happy, they form a lot of biomass and you have relatively little amount of products left over. And if they are not very happy, the bacteria, they're inhibited, the growth is inhibited, you actually have the catabolic ratio of products as a result of the metabolism. So secondly, you could also try to calculate the reaction rate. So this equation just states like a change in concentration in time. which is the reaction rate, is a function of some kind of constant initial reaction rate. Then you multiply that with the yield coefficient, which is this number here for each product or each substrate. And then it's a function of the amount of biomass. So the more biomass, the faster the reaction. And then it's a function of the available substrate. So acetate and nitrate here are the two available substrates. And this equation is called the Michaelis-Menten equation, which can be used to test. It shows that as soon as the acetate goes to zero, this term goes to zero, so the reaction rate stops, and it will not continue when there's no substrate left over. So that's why these two terms are in the reaction rate equation. So using relatively simplistic model, we can more or less predict how much. If we know the growth rate of the bacteria, we know how much products are formed. And with this reaction rate, we can also calculate how fast will it be formed. So that is just the amount of products in moles per liter. But then eventually you want to convert the moles per liter to volume of gas, or the amount of gas saturation. Well, and that is relatively also relatively simply done using the ideal gas law and Henry's coefficient to incorporate for solubility of the gas. So then if you use that, you can actually make a very simplistic model that, depending on substrates concentrations, so this is the concentration of nitrate at maximum growth conversion, this is the concentration of nitrate at zero growth, and you see that actually it's not so much dependent on the growth rate what the volume of gas will be, but it's more depending on the amount of substrates added. So the amount of nitrate will result in a certain amount of volume of gas, and depending on the growth rate, you'll be ranging between these two red lines for a 20 millimole per liter substrate concentration. And it's also highly dependent on the depth of treatment. So if you're 10 meters below groundwater level, you have 10 meters of water pressure on top of the atmospheric pressure, so an absolute pressure of 2 atmosphere. If you feel that pressure here in the ideal gas law, you can see that with equal temperature and equal amount, you will reduce the volume of the gas. So this is a relatively simplistic model to predict the volume of the gas. So then we tried, so that's the theory, and then we said, well, can we then test the theory? So in order to test that, we had to build a modified triaxial test setup. So we could actually treat triaxial samples in a test setup with elevated pressures. So here we can control the sample pressure, we can control the cell pressure, and we can also, by having a hydraulic gradient between the top and the bottom, you can flush a sample with fresh substrates under elevated pressure conditions. So with this modified test setup, we've done a lot of experiments, but one thing is that we could show that the theoretical model which we developed, actually we could use that to fit to the experimental results. And we could also say that based on the theoretical maximum amount of saturation, which we calculated using this kind of equations, we could actually fit the theory, and actually we demonstrated with experiments that depending on the concentration of nitrate as a substrate, you could predict with the theoretical model how much degree of saturation would develop. So that was confirmation that our numerical model for calculating concentrations and products was validated on the 1D column experiments in the elevated pressure conditions. One thing which was not yet in the model, which we found in most of the experiments at relatively low pressures, is that as soon as your gas saturation reaches a certain value, in this case 75% water saturation reaches, or 25% gas saturation, the pores are filled with 25% gas, the degree of saturation doesn't increase any further, and any additional gas would just vent out of the system. So we consider, well, we call this term the gas percolation threshold. So as soon as you reach that threshold, you form a continuous gas phase, and any additional gas which is formed will just vent out of your system. So, and we found that that was actually quite consistent over different pressure conditions. So this is really a property of your sand, of the properties of the sand. The packing and the grain size distribution, for example. Then well, we demonstrated there's limitations to our current model of predicting the degree of saturation, but we also demonstrated the actual mechanical effect. And so we did static monotonic loading on desaturated samples, and we showed that if you increase the substrate concentration, which is shown here, so 25 millimolar, 12.5 millimolar, and 6.25 millimolar of nitrate, you convert from a relatively low diffutoric stress in undrained loading to actually behavior which almost looks like drained loading. And so this is a consolidated drained triaxial test, where this is an unconsolidated or an untreated undrained test. So you by introducing gas in the pores, you will convert behavior from a undrained to a more drained-like behavior. And that drain-like behavior is because the gas takes up the pore pressure, and the pore pressure will actually not build up like it would not do in a drained test. And so that was done on those triaxial test samples, and we also done some cyclic test on that on the desaturated samples, which actually showed that if you have a fully saturated sample, within 20 cycles, you build up pore pressures until you reach almost a pore pressure ratio of 1, which means the pore pressures are equal to the effective stress in the sample, and this is causing liquefaction, which is then shown by the excessive deformation going out of control. This is then the test done on a treated sample, where you see with the same stress conditions, the excess pore pressure actually doesn't build up, because this is the effect of the dampening of the bubbles in the pores, and there is hardly any deformation during that loading. So we've done several tests in cyclic triaxial tests, compressive triaxial test, and demonstrated that by desaturating our sample with just 10% or 20% degree of saturation reduction, we could increase the number of cycles until failure by 25 times, or in the other way around, we could increase the cycle resistance at a given number of cycles by a factor of 2. So that was significant evidence that, yes, we can use desaturation to mitigate earthquake-induced liquefaction. So with that in mind, we started comparing, hey, what is now a good process? We can focus on precipitation. Precipitation, we said, okay, we need 1 to 3% to see some increase in dilatancy and stiffness, which requires quite some substrates, and we need 3 to 10 flushes to get it into the ground. Whereas if you then look at desaturation, you only need 10 to 20% nitrogen gas to be formed, and which only requires, at least, a lot less substrates per cubic meter of treated soil, and everything can be injected in a single flush. So if you then calculate the difference, it's about 40 times less substrate required to desaturate the soil than you have to do to precipitate sufficient carbonate. And so this was the promising pitch for Edgar Zanjan and Sean O'Donnell to state, hey, this is a very promising process. And so we can first focus on the desaturation and then move on to the precipitation if desaturation turns out to be not sufficiently persistent. So, but that brings in the question, so how is the gas distributed and how persistent is this degree of saturation? So further research went into trying to identify how is the gas distributed and is it persistent or not. So we looked at that at several scales. So if you fundamentally look at the pore scale, you can really, you can distinguish different configurations of gas. So the most basic case of which a lot of literature is available is where we have a continuous gas phase with a discontinuous water phase. So this is typically happening in the vadose zone, so in the unsaturated zone above the phreatic surface water. And there we see that actually the gas pressure is equal to the atmospheric pressure. We can have a case where we have both continuous water and gas water. Even here, the gas pressure is still atmospheric. But in many cases where we are working with, we have actually a discontinuous gas phase, and the gas is actually entrapped or enclosed fully by water. So in this case, we have relatively small bubbles, and the gas pressure can be calculated by the water pressure plus the capillary pressure. So here the gas pressure is actually higher. Actually, here the gas pressure is also higher, but water pressure becomes negative. And in this case, the water pressure is positive, but then the gas pressure is higher, with the difference is the capillary pressure, the gas. A final case also occurs. In some cases, the gas bubble can become bigger than the actual grain size. Gas prefers to sit in larger pores, and you can actually see that by this term R. And so the capillary pressure for larger bubbles is actually smaller. So gas wants to move and grow to get the smallest possible pressure. So if gas is a lot of gas is forming, it may fill out the larger pores, or actually it may also create very large pores by pushing the grains aside. And we have seen that in several of our experiments. So trying to understand the mechanics and the distribution of the gas at pore scale, we performed some microfluidic chip experiments. So this is a former PhD student of mine, Dae-Yoon Kim. He injected the substrates into a microfluidic chip and then monitored the gas bubbles, the gas formation and distribution in the microfluidic chip. The microfluidic chip was placed in the vertical position, and gas was able to flow up as a result of the buoyancy. So within this experiment, we found there's two phases. In one phase, there's a single gas bubble initiating within the porous medium, which gradually starts growing and starts pushing towards other pores. So initially it starts in a single pore, and it starts to grow and expand into multiple pores. And every time it passes a thin pore throat between two larger pore bodies, you would see a drop in the pressure. So these pressure drops are called Haynes jumps, and that's typical for gas migration in porous media. But at the pore scale, there can be a lot of pore pressure fluctuations. So, but yeah, one reason why there was only a single bubble growing is because the gas is actually formed very slowly. So once you form gas very slowly, you have a single bubble somewhere in the porous domain, then all the gas can diffuse towards the single bubble instead of forming a new bubble. And this is because there's a threshold of gas bubble formation. And so for gas to go from the liquid phase to the gas phase, you have to exceed an energy barrier. So then it's more energy. It's better. It requires less energy to diffuse to an existing bubble than to form a new bubble. So in the second part of the experiment, about 5 days into the experiment, we see a sudden, very rapid decrease in degree of saturation, up to about the 75%, which we considered as the threshold for gas percolation. But in this case, this significant reduction in degree of saturation was not due to the formation of gas within the domain, but it was actually due to formation of gas below the domain at the boundary. And because this was all enclosed, the gas which was formed here was then pushed through the permeable zone, and actually particularly along the boundaries of the domain. And then that resulted in a reduction of degree of saturation down to 75%. And afterwards, we saw a lot of events where it went up and then gradually down, and then suddenly up again. So suddenly up meant that the gas which was close coming to the exit boundary was venting out, and suddenly all the water filled back the pore spaces which were left behind by the water. So we get water flowing back in. So you can see here that, well, at the pore scale, the presence of the gas is both a function of formation of gas and migration of gas. That was the main lesson which we learned from this microfluidic chip experiments. Another thing we found, looking in closer detail to the single gas bubbles in the microfluidic chip, we could identify many different mechanisms of gas migration. One is just the formation of a single bubble, then migration into a second pore just by growth. And then here you can see many different movement types. One was very nice. It was like a snake moving upwards through the domain. Just because of the buoyancy of the gas, it gradually moves up, but then because it's well, the size of the bubble is more or less fixed, it just migrates like a snake through the pores. But then, well, that wasn't the pore scale. On the other hand, we're testing and we're trying to implement this process at a large scale. So in order to assess the migration of the gas at the large scale, we built this large scale two-dimensional tank test, which is like 1 by 1.2 meters and then 5 centimeters in width. And we filled that tank with different layers of sand. We also wanted to assess, well, how does gas migrate in an homogeneous soil or in a stratified soil, and what's the effect of stratification on the distribution of the substrates, but also on the distribution of the gas. So here we had embedded several sensors, and these are sensors which can measure both the electrical conductivity and the volumetric water content. And we buried them in the coarse grained sand, and we buried them in the fine grained sand. And we also, well, we took pictures every 10 minutes of the screen as we were injecting. And first we did a single flush where we added some food dye to the liquid to follow where the liquids would flow through the domain. Afterwards, we did one reaction flush, or we did one treatment with food dye, and then we did several flushes of water to check the persistence under heavy groundwater flow, lateral flow. And after that, we did 8 additional flushes to look what would happen if we would try to cement this heterogeneous soil profile. So what you see here is just a flush of water going into the tank. So clearly you can see the difference between the high permeable zone, which is the coarse sand, and the low permeable, well, lower permeable zone of the fine grained sand. So here you can actually see that the delivery of substrates is really depending on well, permeability of the different substrates where you flush through. So we inject on the left and we extract on the right. But then when we started injecting substrates instead of just water, we see some different phenomena occurring. So first of all, you could see, and I think the movie will repeat itself, you could see that the water flush was just filling the entire coarse grained sand layer, while the substrate flush shows an inclined front of substrates going through the tank. And we saw also a lot of flow going downward into the finer grained sand layer. So the inclined front and the fingers going down into the fine sand is actually a result of the gravity. And remember that this is a very low concentrated injection. So it is only 25 to 50 millimolars of substrate concentration. And even with this low density in a coarse grained and fine grained sand, you can already see that there's quite some effect of the gravity on the flow within the system. Second, once the reaction starts going after 2-3 days, you actually see that oh, it's now getting stuck. Oh. You can actually see that even though very limited substrate, okay, let's go back 2 more steps. So you can see after day 2 or 3 that gas starts to form, and then once gas starts to form, you can see there's a lot of movement of the gas going upwards and pushing the liquid in front of it. So even though the zone here close to the outlet didn't receive a lot of substrates, due to this gas formation, you get a lot of convection through the system. So eventually, due to gas migration, eventually the entire tank was partially desaturated. And we could demonstrate that from the actual measurements. So I hope it's not going too fast now. So these are the measurements of those embedded sensors. And on the left side, we see the sensors embedded in the coarse sand. We see that during the injection, they all receive substrates, and within 2-3 days, So this is the leftmost sensor, this is the rightmost sensor, and this sensor is in the middle. And within 2-3 days, all of these substrates are being consumed, and as a result, electrical conductivity is reduced. And within 3 to 4 days, all substrates are consumed. And there's some residual substrates because the consumption was a bit out of balance, and acetate was not consumed as fast as the nitrate. Whereas in the fine-grained sand, we only see substrates in the leftmost sensor. The other two sensors didn't receive a lot of substrate. So because there's no substrate, there's hardly any reaction there as well. Although we see that after 2 to 3 days, they receive some substrate, but this is then the substrates which are pushed forward by the formation and migration of the gas. Looking at the gas, we can actually measure the degree of saturation. And on the leftmost one, you can see almost immediate reduction in degree of saturation below 70%. But in the coarse grained sand, it's all between, well, 72 and 65% degree of saturation. So this is actually higher than the degree of saturation we saw in our column test. And one reason for that is because on top there's a finer grained sand, and there's some resistance of the gas to go through that finer grained sand. So still we see here the degree of saturation for the fine grained sand is a little bit higher than in the coarse grained sand. And this is because there were lower substrates, and particularly on that right corner of the fine grained sand. So the degree of saturation you get there is just purely by gas migration and not additionally by gas formation. Looking at the water flushes after the treatment, we can actually see that well, you remove quite a lot of the gas, but not all the gas is removed, and there's a residual degree of saturation of 82 to 95%. In the finer grained sand, the removal of gas is a bit more efficient as a result of the water flushes, because probably the formation of gas results in isolated pockets of gas, whereas the migration of gas has continuous gas paths, which are then more easily removed than the entrapped and closed isolated gas pockets. But overall, the gas is persistent after several flushes of water. Looking then what happened within that reaction period, so after all the reactions were consumed, at the pictures we see a lot of things are happening. And this is interesting because this shows that starting to induce biochemical reactions by injecting some kind of nutrients actually affects the entire ecosystem. So what we think is happening here is that as soon as the nitrate is consumed, so here in blue you see the additional water flushes going through the tank. But as soon as all the nitrate is consumed, there's some leftover acetate, which is then anaerobically digested to form methane, and probably maybe also some anaerobic products. And the black stuff, which you can see then developing, is anaerobic biomass or anaerobic, well, minerals. Could be pyrite, which is also black. But it just indicates that all the black zones are anaerobic, so there's no oxygen present. What you then also nicely can see is that as gas which is formed below is venting out, water will go back in, and gradually the water level will drop to fill out the water level which was initially up here in the tank will gradually drop. You can also see that there's some desaturation happening as a result of the water dropping and the gas venting from the deeper layers. So which means if air has to enter here, because water is draining downwards, air comes up and air contains oxygen, so that oxidizes the anaerobic biomass in that system. So the main message here is if you start playing with bacteria, you enter a very complex ecosystem, and you have to actually consider all those complex reactions as a result of injecting some kind of nutrients in the ground. This is actually results of some very recent experiments which are not published yet. So we repeated the same thing, but now with silt and sand layers, and we only inject in this sand layer here. So this is a fine sand and this is a silt, and then another fine sand, but which is not injected in, and then another silt. So if we looked quickly at the video here, we can see now as we inject the substrates, there's actually less gravity-driven flow, and that has, well, that's one reason for that is that the grains are finer. So the finer the grains, the less the gravity effect. And the second feature you can notice is that there's hardly any flow going into the silt layer. So here the ratio of permeabilities between silt and sand is much higher. So therefore there's a much more confinement of the liquid during the injection. If you then look later in the experiment, when we have gas formed, and this is actually a second flush, there's some other nice features you could see, is that here at top of the sand layer, you see some kind of sand volcanoes, which we feel are silt volcanoes in the sand, which we hypothesize that this is due to gas seeping through the silt going up into the sand. And another evidence of the gas venting and seepage through the silt is that we see this burping of the upper silt layer due to the accumulation of gas at the top of the upper sand layer. But we measured the degree of saturation in both the upper sand layer and the silt, and both show hardly any change in degree of saturation, which indicates that the gas which seeps through the silt is actually very tiny gas streams or tiny gas bubbles, which then easily migrate up through the sand and do not get trapped or desaturate the upper silt layer, which hasn't received any substrates. All right, so that was the largest scale experiment. So the final thing we did, and actually it's not the final, so the previous experiment we did after we've done the field trial. So having all these results, we got in contact with the group at Portland State University, and they have actually a large incentive to come up with a solution to earthquake-induced liquefaction, because the entire city of Portland, at least a large part of it, is situated on these silty alluvial sands, which are highly susceptible to liquefaction in case of a heavy earthquake. So they managed to receive some grants to perform a field trial on this process. And we selected two sites, one very close to the Portland International Airport, and one here at the Harpenden site, which is one of the areas in Portland where a lot of oil storage tanks are situated on a liquefiable sand layer. So they pitched it like, well, if we don't do anything and we get this big earthquake, then all the oil reserves of the state of Oregon will flush into the river and cause a huge environmental catastrophe, but also a huge logistics and economical catastrophe. And if it would liquefy underneath the airport, well, if the airport would not be functioning during in case of an emergency, you have a huge hazard on top of the already big hazard of an earthquake in the area. So with that, we said, okay, let's try and set up a field trial. So here, same concept, but then a bit larger scale. We inject a treatment solution. So first we had a mixing tote where we mixed all the calcium acetate, calcium nitrate, same recipe as we used in the column. We mixed it prior to place it in the injection container. From there we used a pump to pump it into the ground, using a filter from 1.5 meter to 6 meters below the surface. And then we had monitoring rods for seismic velocity in the ground. We flush it towards the extraction wells, and the extraction wells are placed to keep a constant head and extracting the liquid into the extracted groundwater container. We measured the salinity both in the tanks, and we measured the salinity and volumetric water content in the ground as well. So we found the soils where we placed our sensors and wells were situated in a low plasticity silt environment. And well, we targeted about 200 cubic meters of sand with a treatment range of 3.5 meters. So looking at those results, in total, we injected about 70 cubic meters of substrates into the ground, and we could follow the electrical conductivity. And here you can see the electrical conductivity of the injected liquids and the electrical conductivity of the extracted liquids, where you see, well, the injection is much higher than extraction, which means that most of the nutrients injected are converted, and we can actually do a mass balance to look at the difference to see how much of our substrates are converted and try to estimate and fit our numerical models which we're developing. The fact that you see an immediate a peak here immediately after starting a new injection indicates that there's actually some rapid breakthrough of those injected substrates, which can indicate some preferential flow through some higher permeability layers. And the same is visualized here, is that we see an increase in the EC in the extracted liquid compared to the EC of the injected liquid, which indicates there is some breakthrough. Within 4 hours, we already see some of the liquids on the other side in the extraction well. Looking at the in situ monitoring of the electrical conductivity and the degree of saturation and the pressure wave velocities, we do see a reduction in the degree of saturation after about 20-25 days. And we stopped about 40 days of treatment. Also, we see some continued reduction in degree of saturation in the later stage, which could be either due to compaction of the soil or due to a continuing reaction, which is relatively slow. Looking at the pressure wave velocities and knowing that the pressure wave velocity is affected by the degree of saturation, particularly between 100% and let's say 95 or 90%, the pressure wave velocity is highly sensitive. So you can really detect with the reduction of pressure wave velocity indicates a reduction in degree of saturation. So here we can see that within 25 days of treatment, we see a significant reduction in the pressure wave velocities at the different depths. Actually, at the top, we already see a low pressure wave velocity because this one is situated in the unsaturated zone. But the deeper sensors, which are situated in the saturated zone, they show a large reduction, indicating that that we're actively desaturating the soils. And we also saw that afterwards they remained low, which indicated, in this picture you can actually see 120 days, but in the paper we recently published on the topic, we demonstrate that actually after 600 days it was still a reduced pressure wave velocity in those locations. So at that site, after treatment, we also tried to simulate an earthquake by putting a large shaking machine on the ground. And here you can actually see the shaking of the ground and how significant it is. However, the results which came from this experience, because we buried a lot of accelerometers and pore pressure sensors into the ground, are still inconclusive and currently being analyzed. So I cannot share anything there yet. One of the questions about persistence, we've demonstrated in the field that the bubbles, once they're in there, they remain there for at least 3 years. But also some other colleagues, they developed a model which they can actually predict the persistence of the gas. And they assume that, let's say, if you have an entrapped gas bubble, and it cannot migrate because it's too big to squeeze through the pores, it can only be removed by groundwater flow, dissolution, and convection and diffusion of the gas into the groundwater phase. With this model, it's again a reactive transport model, they could demonstrate a persistence of reduced degree of saturation for multiple years, up to 100 years, depending on other things like the gas type, the depth, the bubble size, boundary conditions, and the amount of groundwater flow in the system. So we're moving forward towards getting a better understanding and also more theoretical backing of how persistent the gas is under different conditions. So with that, I'd like to conclude to state that microbially induced desaturation can be used to desaturate granular soils and mitigate earthquake-induced liquefaction. And secondly, the desaturation is significantly cheaper than precipitation, so it's really low-hanging fruit in order to commercialize and try to get real projects ongoing. I think I've shown several numerical models which have been developed to calculate the distribution and persistence of the gas, but they still need to be improved. And we've demonstrated persistence, but then continuing challenges is really to control and assess the substrate distribution and reaction rate, particularly in the context of heterogeneous soils and stratified soils, as well as trying to assess the mechanical response, including its effect of heterogeneity. So what I mean there is that if you know that the gas is heterogeneously distributed in a heterogeneous soil, so it preferably sits in the coarser sand layers and doesn't go into the silt layers, at that moment, how does such a stratified heterogeneous soil respond to any earthquake shaking? So that part still has to be investigated. Also, the models which I showed were very basic. They don't have a gas percolation threshold and they don't incorporate multi-phase flow, so there's significant development required there in the development of those models. So So far, I only talked about earthquake liquefaction mitigation, but we have been looking into other applications of desaturation. For example, you could desaturate the soils to reduce the water content and bring it closer to an optimum water content so you can improve the efficiency of dynamic compaction. But that's then time for another talk, maybe. And the second challenge is commercialization. So what I find, well, biogeotechnics is still a lot into the research arena, but there's still limited amount of successful commercial applications out there. So, well, one of the reasons why I joined a commercial company is also to get that established. So with that, I would like to thank all my co-workers on these projects I have been showing, and I'm really open for any questions.
Thank you very much, Liang, for a very interesting